Okay, we left off discussing light, and we know that light at this point has dual properties. We know that it is a wave, such that c is equal to nu times lambda, and we know that it is a particle, which we call a photon, such that the energy is equal to nh nu. So, with this in mind, we also realize that we had the Bohr theory of the atom. In Bohr's theory, he said that an electron is a particle and it exists in orbits around the nucleus. And that is where we left off. We knew that the Bohr theory was a failure, that the electron as a particle sitting there in orbits around the nucleus does not explain any atom besides hydrogen, and that we know this about light. Louis de Broglie took it the next step, and what he said was that electrons or any particle can also be waves. So let's sort of think about duality for a second. If waves, like light, can be particles, then particles, like electrons, can also be waves. All right, Louis de Broglie took this the next step, and he said that electrons are particles and waves, and we could actually calculate the wavelength for these particles. Our units are particular because our h is in units of joules. A joule is a kilogram meter squared per second. So our units have to be such that the mass of whatever it is here is in kilograms and our speed is in meters per second. So let's do an example. We want to know what is the wavelength, what is our lambda for an electron traveling about 1% of the speed of light at this speed. So our equation is straightforward. Our wavelength is equal to h. We know h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds, divided by the mass of the electron we can look up, 9.11 times 10 to the minus 31 kilograms, times the speed that this particle is traveling at, and this is given as 2.2 times 10 to the 6th meters per second. So, what cancels? Well, because joule is in kilograms meters squared per second, our seconds are going to cancel out, or both actually seconds squared will cancel out, and we are going to get an answer in the unit of meters, and it is going to be 3.31 times 10 to the minus 10 meters. Now, when is this relevant? The de Broglie wavelength is only relevant and only measurable if we have something very small, such as an electron, moving very, very, very fast. And then we get a wavelength such that we can actually look at this. Now, has this been proven? Yes, because we have experiments to show that this is the case. This is a diffraction pattern for electrons. It looks almost exactly like a diffraction pattern for waves. And if you go to the next slide and you watch the video, it's about the best explanation I can come up with on how this works. All right, so watch this video, please, and see Dr. Quantum discussing electron diffraction. The only way that we can get a diffraction pattern, such as the previous slide, is to assume that electrons are waves. So where does this leave us? This leaves us with some pretty serious issues because what do we have? We have electrons are particles, and we know that they're particles. We know they're negatively charged. We know they have mass, but around the atom, they do not act like particles. Around the atom, we have to make a new assumption, and we have to assume that electrons are waves. Now, we can show that our electrons are waves because we can do an experiment that proves this. But what does this mean about what do we know? Because if we are going to take, and by the way, we started this whole thing out with asking the question of what is an electron? And we said, all right, we knew that they were particles, but now we are going to have to work with waves. Where are the electrons? Well, to know where electrons are, we have to stop and do some physics on them. So let's think about waves, and let's think about in the simplest sense. we want a good explanation, please watch this video on the Heisenberg uncertainty principle. Otherwise, just think about it very basically. And that is if an electron is a wave. And we have to ask the question of where is it? We realize that it's very hard to quantify the actual position of a wave. We simply know it is here somewhere. And Heisenberg took this to a very good mathematical position. And what he said was, it is pretty much impossible to know both the position and the momentum or the speed of an electron at the same time. Therefore, what do we know? We know pretty much nothing. Either we know where it is, and have no idea how fast it's going, or we know how fast it's going, but we have no idea where it is. And that is where the Heisenberg uncertainty principle leaves us. So let's remember where we are. We know that in waves, our energy comes in amplitude, and we know that in light, our energy is in the frequency. We know that if we have an electron going around the nucleus, it has a fixed space it can be in, and therefore it is going to be a standing wave. So this is our electron around the nucleus, and it's a standing wave, which means it is quantized. So what do we have here? We have quantized waves existing somewhere around the nucleus. Ignore the panting, that's just a dog. This didn't bother the physicists because Erwin Schrödinger said, I can do this. Here is what he assumed. He assumed that we have the hydrogen atom, and by the way, this has only been solved exactly for the hydrogen atom, and that we have one proton and we have one electron, and this electron is in a wave. It is going to be quantized, i.e. only certain energies. And what he said was, if we have the nucleus here and we have the electron, and the electron is out here somewhere, it is a wave, and he put rules on it. He says it can't be in the nucleus, and if you pull it far enough away, you're going to lose it completely. And that is all he did. And what he came up with once he did that was a nice set of quantum numbers that described the position and the probabilities of finding the electron around the atom. All right, so what do we have? We have a piece of metal, and they have sprinkled some sand on this piece of metal. It's sitting on top of a speaker such that the frequency of this sound is increasing. Now, because it is on a piece of metal, this has a fixed set of ends, which means that anything that's going to exist on it is going to have to be quantized. Again, meaning only certain energies, and you see that as it goes through and it comes up with very distinct stable patterns. And there are not multiple in-between patterns. It just bumps from one stable pattern to the next, and that is quantized. When does that happen? It happens when you have a fixed set of ends that something can exist on. So watch this video and recognize again that sound on this speaker or on this piece of metal is going to be quantized. Please note, electrons around the atom are waves, and electrons are going to be quantized. So what do we get out of this? What we get out of this is kind of what we saw before with the Bohr equation, except that this one actually is going to work. We are going to have orbits, except they're no longer going to be circular orbits with a particle existing in a circle. They are going to be waves. They're going to be a set of probabilities where we're going to have a likelihood of finding this electron in this space. We are going to get orbitals, and we are going to be able to describe where the electrons are. The actual equation for this mess is really difficult, and instead of looking at the actual equation, we're going to look at an address system. And our address system are going to be a set of quantum numbers. And we will do those in the next section.